page number 75. Now, and last Thursday we discussed how to calculate, how to determine the moment of inertia of this shape. And for your reference, and in the future, you will use the moment of inertia of several shapes. And for a rectangle, and if the reference axis is x prime here, if the axis is x prime here, that the moment of inertia is how b times h cubed over 12. So b is the width of the rectangle, and the h is the height. If the axis is x prime here, which goes through the centroid, and if the axis is y prime here, now, and of course you can imagine the moment of inertia will become the width of the rectangle will become h, and the height will become b. So for y prime, that for the axis y prime, that the moment of inertia will be h times b cubed over 12. So it is. I usually remember it like this. And I for this h cube, and because and we take a look of this x prime and h cube. So the direction of x prime is the direction of x prime in this case, x prime is perpendicular to the direction of h of cube. It's okay. So I usually remember it like this: if the direction is perpendicular to our reference axis, because our reference axis here is x prime, so the perpendicular direction is the h direction. So you have h cubed. But if we are but if we take y prime as the reference axis, the direction that we need to put cube is this one, because it's b, because the direction y prime here and the direction of b is these two are perpendicular to each other. So that is but of course in the future in the future, that if you have many if you do more exercise, that you will remember. And for a circle, and for a circle, we have the moment of inertia about x-axis and y-axis being equal, and these are pi r to the power 4 divided by 4, and because you can see the shape is about x-axis and about y-axis are the same, so the result should be the same. Okay. Now, and I want to introduce one more term. This is called polar moment of inertia. polar moment of inertia here. This is with respect to a point. With respect to a point. In this case, in I let me show it to you. For I that it is equal to x squared dA integral, and Ix is equal to y squared dA integral. So, but in this case, polar moment of inertia, we usually call it J with respect to O. It is equal to R squared dA. R is the distance from the point of reference to a certain area. And it is equal to, for a circle, it is equal to sorry, I should put it U here. I think it's easier to do the rest. And for dA this case, what is the magnitude of what is dA in this case? dA is equal to 2 pi u squared times du, right? Sorry, 2 pi u times du. Therefore, it is equal to 2 pi u squared du, and then it is from 0 to R. And of course, you can get it. You can get the answer here. Is that okay? Oh, sorry, it's to the power 3. It's 2. Sorry. It's okay. Now, because u squared is here, and then dA equals to this one, and then we get this. Now, and for the next part, and it seems that we have three things. We have Ix, we have Iy, and we have Jo here. Are these three things independent? The answer is no. Let's take a look of one arbitrary shape, any shape. And then, for example, if our dA is this thing here, if our dA is here, and then we have point O here, and of course we have U is here, right? U is this one. Okay. Now, and but U can be written in of course we can write these two, right? And it has x coordinate and y coordinate, and of course we can write x and y like this. Okay. Now, if we write like this, and JO can be written in the U square can be is equal to x squared plus y squared dA. Okay. Because U square is equal to x squared plus y squared. Then what is it? Then it can be written as I y plus ix. So if in the for any shape, if you know ix and iy, and then afterwards you know what is JO here. Now this is equation 9.4 on page 489. Yep. Equation 9.4 on page 489. Now we want to I want to please take your time to write this, and I will talk about the last thing in the course. And after you finish writing this, then you can go to the next page. Now we go to the last theorem in this course. It is called parallel access theorem. On the next page. And the theorem is like this. I have mentioned that when we write moment of inertia, we always need to write the axis of reference, right? And for this for the theorem, it is like this: x prime plus b squared. And in the examples, I have in the examples and in the table, I've told you ix prime is equal to bh cubed over 12. But we can, but if you do the same math, you can know you will get this. If we take the reference axis as xb, then ixb is equal to bh cubed over 3 only. So it is not bh cubed over 12. If we if we take any other axis, the value will be different. Okay. So then how do we? But we don't want to do the integration every time. We don't want to do integration every time. So this theorem is like this. This one, I should mark it in red. This one is with this moment of inertia is calculated with respect to something we call centroidal axis. This means the axis through centroid. Okay. And of course, in this case, is C. Now, if we have and then for this equation, A is equal to the area. A is equal to the area, and D is the distance between x prime and reference axis. So if we take the reference axis here, then D is this one. If we take it here, then D is this one. And from here, we may say you may notice one thing. From here, you may notice one thing that this part is greater than 0, right? Because this way is positive and A is positive, so A is positive, D is not negative, so Ix is greater or equal than Ix prime for any axis. I will show. I'll prove that in a minute. I'll prove this in a minute. And let's after that we work out an example. to show I want to show the relationship between this and this. I want to show the relationship between ix prime and ixb in an example. Now we are and from the notes I've told you, ix prime is equal to bx cubed over 12. And for let's do in the usual way of finding ixb. For ixb, that the reference axis is xp here, and for distance here we have yb here, right? And suppose we have xp and yb here. Now, then the distance yb is of this area, the A is from the xp axis is yp. Okay. Now we have that is yb square dA. Therefore, and dA is equal to b times dy. Now we have therefore we have and yb cube and then b times yb, and then we integrate from 0 to 6. Then I think you are able to get the result is bx cubed over 3. I think you can do this. I think you can do this. For the next part, we want to start from here. We want to do now everything is written in yp, but now we want to do a variable. We want to change the variable. We want to change the variable from yb to y prime. It's okay. I think you have done it in calculus. But now let's do it here. Because for any area here that x prime, it has a coordinate of x prime, y prime, or xb, yb, right? We have x prime y prime or x b y b for any area. You can write it either in this way or this way. And I think from the figure you can know that yb is equal to y prime plus half of x, right? Because if yb is equal to 0, y prime is equal to negative half of x. If yb is equal to x, y prime is equal to half of x, and so on. Then, of course, you can get this one, yb is equal to y prime plus half of x. And for any dA for that shape, the area is equal to b times dyb, but actually it's also equal to b times dy prime. Does it sound reasonable? Because one unit of the yb is equal to 1 unit in y prime. So, and to get to change from yb to y prime, we only add or minus half of x. The relationship between an area, a coordinate in yb and coordinate in y prime is like this. Now, we want to rewrite this. We want to rewrite this into this. Let me put an arrow here. Now, it's like minus half of h and half of x, and then this is y prime plus half of x squared b dy prime. It's okay. If we get this, then of course we can write it in 3 terms. We can break it up into 3 terms here, and then we do them one by one. Now, if we and from here, let's take a look of each term. This one, and if we get if we look at the page if we look at the page 70 and page 70, I think page 74, and it is equal to Ix prime, and Ix prime is through point C. And for this one, and for the last term, it is because H is not related to Y prime, so it is equal to B dy prime. It is equal to half of H times 8, because it is simply equal to the small all the A added together. So it is the area of the shape. And the only thing I want that is a bit more difficult is this one. So let's take a look. And for this, the term in the middle, that H is, of course, as I've said, not related to the integral, so it can be put away. It can be taken out from the integral. So, and this one B dy prime is equal to dA. So we have y prime dA here. Then what is this? From chapter 5, we can get this one is equal to y bar prime 8. This is from chapter 5 because this we get the centroid of shape from here. Right. Then from here, what is y bar prime? Y bar prime is the centroid of y in this x prime, y prime coordinate. But since it goes through the centroid, so this one, this one is equal to 0, so this one is equal to 0. So from here we can get, what do we get? Ixb is equal to Ix prime plus half of x squared times 8, which is the parallel axis theorem.